Hi, it's Robin. This is a follow-up video to the previous one about Truchet tiles. And in this video, we're going to be doing a code walkthrough of my little Truchet tiles program. So I suggest you watch the other video for context here. This one is just going to be about the code. So there's a downloadable D64 in the video description. And it's Truchet.d64. I'm using a micro IEC in my Super Snapshot cartridge, and so we can mount that disk image like this, or if you're using an emulator, just drag the D64 in. You probably know how to mount a D64 if you're using other hardware. Okay, and we'll just press F3 to do a directory, and this disk has Turbo Macro Pro on it. And several different versions, or many different versions of the source code. The latest one, as of when I'm making this video, is tile 21. Check the disk directory and video description in case I update this further. We can load the Turbo Macro Pro assembler, TMP, 8, 1, and it'll load. And that can take a little or a long time depending on your configuration. Once it's done, SYS 32768 to start Turbo Macro Pro. If you can't remember the file name, back arrow asterisk will do a disk directory, and our source code file is tile 21. Back arrow L to load it. Tile 21, press return. It loads in. And there's our source code. Even though I showed it, might as well run it really quickly here. Back arrow 3 to build, but don't press S to start because I'm using this basic stub. Anyway, the auto start doesn't work. I'll explain that in a moment. Back arrow 1 to quick to basic. And you can see that the basic program's there and we can just run it. And as I explained in the other video, there are 30 different patterns. Just press return or actually any key to cycle through them, and each one is generated from a bunch of data that I typed into the program, tile patterns which are then repeated across the screen, and the tile pattern sizes and the data of course vary. So that's what we'll be looking at today, how the program works, how it displays these tiles. And even if you don't find the patterns interesting, maybe you'll find something in the source code interesting or educational. Okay, there, we've looked at all 30 patterns. To get out, you can just hold down stop. It'll actually cycle, and tap restore. It'll go back to the basic prompt where we can again type sys 32768 to re-enter Turbo Macro Pro. Okay, we'll walk through the source code here. I've shown this before. This is what's called a basic stub. So star equals 0801, and that is the beginning location of a Commodore 64 basic program. And what we're doing is kind of simulating a basic program to make this program runnable. Actually, I can go back arrow load. I think the previous version called tile 20 or 20 is before I added that basic stub. Press shift F1, that is F2, jump to the top. And you see, while I was developing the program, I actually had star, that's the origin, 1000 hex. And then it would jump to start, which just jumps past all this down to this, the start of the code. I'm just explaining that you don't have to have that runnable program. When you're developing, you might find it easier just to do this at a different memory location, back arrow 3 to assemble, and then that S will just automatically start. And there's our program. 32768. Actually, if we go back arrow build, you see it's actually assembling into memory from location 1000 hex to 1477. That's just matching where we set the origin here. If we assemble and go out, then we can also start the program with sys decimal 4096 is the same as hexadecimal 1000, or hex 1000 as I sometimes say. So you can also start the program that way. Okay, back into the assembler. And we'll load up the latest version, tile 21. I just want to explain that in case that seems helpful. Okay, so we've changed the origin to 0801, which is where a basic program is. Then we have define a word of 080B. A word is on 6502 is a 16-bit address, and that points to this location, 080B. And this whole stub is just, like we were saying, to start a basic program. So we're telling it to assemble to location 0801. So there's 2 bytes, 0801 and 0802. Then there's 2 more bytes, 2024, that's the line number. And it's just kind of a tradition to use the current year as your line number in these sort of low basic stubs. So those are going to assemble at 0803 and 0804. This 9E hex is the basic token that represents the sys command. So we've got our basic line number, the sys command, and then the text 2061 is the address that the sys command will jump to. And 2061 is going to point to this jump start. Then we have a 0 byte to terminate the above line of basic, and then 2 more 0 bytes to show that we're at the end of the program. And that's what this 080B is. This is a pointer to the next line of basic, and we tell it that's the end of the basic program with a pointer to 00. Okay, I've spent quite a while just on that. You don't have to understand that, but that's an explanation if that helps you understand. And then the first line of code is just jump start. And I've done that so that I can have some various definitions here. Some of this, like all these 0 bytes here, you don't want the CPU executing them. They're just data. So we're going to tell the program to jump over ahead to the label called start down here on the other side. If you don't like that, you could put all your byte definitions at the end of the program or somewhere else, but there's times I like them being handy at the top of the program. I should say right at the beginning, this code is not particularly optimized. It's not deliberately inefficient either, but I just tried to make it just kind of straightforward for the purpose of learning. It's fast enough for the purpose. Why optimize more? That's not what we're doing today. So, I mean, if you want to leave comments about how all the ways this could be optimized, that's fine. But I just want to say I'm not very interested in that for this particular program. Okay, now there's a number of definitions here. SCR is short for screen, and this is screen memory. This very screen that we're looking at, the text screen, is located at 0400 hex or 1024 decimal by default, so we'll just use that. That can be reconfigured. Color memory is at D800. These are just defines. It's like setting a variable, but it doesn't change because it's constant. It's just used at assembly time. And now here's the screen W for width. Screen width is 40, and screen height is 25. That's the regular 40 by 25 C64 screen, 1,000 characters total. The number of patterns, Truchet patterns, there are 30 of them, so we're setting that. And now we have 2 0-page pointers that we're going to use a lot. One is a pointer to the screen where we're going to render the tiles to. Another pointer that points at the pattern in memory that's going to be replicated across the screen. For these pointers that we're going to be using with indirect indexing, they have to be located in 0 page, which is the first 256 bytes of memory. That's why they only need an 8-bit address, because they're assumed to be in the first 256 bytes of memory. And the C64 operating system and BASIC leave these 4 bytes available for the user. It's possible to use more of 0 page, but we didn't need it. Okay, now there's a long list of what we could call variables or reserved memory locations. They're being assembled here in program memory. That's fine. Data and code can coexist in the same memory space on the 6502. It makes no distinction for that. Some of these could be moved to 0 page for a bit more speed, but I don't really care. So we're going to be seeing more of these later, but just quickly, this is the screen X and screen Y position. We're going to be tracking them as we draw the screen from the top left corner. The current pattern number that we're rendering, that's from 0 to 29. Pattern X and Y, so within each pattern, it's almost like a little, not a bitmap, but like a little screen, and we have to track our progress in there as we draw it to the screen over and over again. We're also going to track the pattern width and height, so we know when the pattern is going to wrap around, that same pattern is going to appear many times on the screen. Some patterns might just have a width or a height of just 1 or 2, and as we saw, some of them get very big, like 12 by 12, so the same code can handle all those different sizes. So that's pattern X and Y is the progress within the pattern. Pattern width and pattern height, H. I know it looks like the word path. That means pattern height. And the pattern low byte and high byte that's also a pointer to where the pattern is in memory. We're going to need to reset that periodically. So we're going to save that rather than recalculate it over and over again. And each of those is just a single byte. So an 8-bit value between 0 and 255 decimal, 0 and FF hex. And this is the tile definition. In the previous video, we talked about how there's 4 different tiles. It's really the same tile with 4 different rotations. These are the Petsky values of those. Character 223 points down to the left, if we're thinking of that little triangle as an arrow. 105 points up and to the left, 95 points up and to the right, and 233 points down and to the right. If these numbers seem kind of random, well, that's just where they happen to get assigned in the character ROM character set. So that's kind of like a translation table. We're just going to be using the numbers 0 through 3, and Truchet himself used A through D to represent those 4 different ones, but they have to get translated into Petsky. That's what this table's for, and we'll see that more later. Now our program is finally starting. Start a pattern number. So we're just going to initialize some variables here. We're going to normally start at pattern 0 and store that in the pattern number. For the sake of debugging, I sometimes change that, like when I was working on those tricky ones, I might set it to 24 so then I could just run and I didn't have to flip through all the different patterns. I could immediately look at pattern 24 and make sure I got the data for it right. Load A with number 21 and store it in this 53272, which is a VIC register. That's just making sure that we're in uppercase. Turbo Macro Pro by default is in the lowercase mode, which is fine, but the graphics that we need, those various triangles, those tiles, are only available in uppercase, or I think they are. So normally when we turn on Commodore 64, you're in uppercase. Turbo Macro Pro and other programs might switch it to lowercase, so it's good practice to force it back to uppercase just in case. Okay, now medium gray border and a white background. So color number 12 is medium gray. And I just use that as the border halfway between black and white, roughly. And color number 1 goes into the background color. So whenever you see the white part of a tile, that's actually just the background. showing through the transparent part of the character. And now actual color memory, we're setting here black characters. So we're going to load the accumulator with color 0, which is black. We're going to load the X register with 250. We have 1,000 locations on the 40 by 25 screen to fill. So the reason we load 250 is because that's 1/4. It evenly goes into 1,000. We can't load X with 500 or 1,000 because that is larger than what will fit in an 8-bit value. The maximum we can load into X is 255. So we do 250 because that's exactly 1/4 of 1,000. And we can split the fill into 4 different pieces. Now right away we decrement X. This is a bit of a trick to 249. Each X is what's called an index register. It kind of reaches from a base memory location. It can reach up to 255 characters away from that. So when we store A, that means store color black in location color, that's D800, which is the color memory. Comma X really means plus the contents of the X register. So it's reaching, well, 250, but we've decremented X by 1, so 249. It's reaching 249 characters beyond color memory. Next, we're going to also store that color in color memory plus 250. That's done at assemble time. And then the X register is added on. So what we're doing, and you see we've added 500 and 750, kind of segmented the screen into quarters, and we're doing 4 stores simultaneously. If we consider the beginning of color memory character 0, character 249 is going to get filled. 249 plus 250 is 499, 749, and 999. So those are 4 spots. And then if the decrement did not reduce X to 0, we're going to branch if not equal back up to loop 1, which will decrement again to 248. So you can see this loop just happens 250 times. It will fill, put a 0 in memory and decrement, and all 4 of those will kind of move backwards through memory. The reason we go backwards through memory, often in 6502, when you decrement down to 0, that sets a 0 flag which can be detected with this branch if not equal. So 0 is very useful because it gets automatically flagged without having to do a compare. If that didn't happen, we would have to do something like compare X with 0, and that would burn some extra cycles. So again, this is an optimization. We're doing the decrement first so that X is equal to 0 while we're doing all these stores. Now note this only works when you're doing stores because stores don't affect the 0 flag. We can decrement, the 0 flag gets set, and we can do all these stores without affecting that 0 flag and then finally check for it. If we were trying to loading A or loading any register does affect the 0 flag. So instead of detecting that X decremented, we'd be detecting if our loads, any of them were 0, and the loop wouldn't work properly then. Okay, moving on. Okay, now we need to get the pattern pointer. So init draw, this is the beginning of the actual draw. We're going to load the current pattern number, so it could be 0 or 1. We increment it as we press a key. So we load the pattern number, we do an arithmetic shift left, and that is the same as multiplying by 2. It has no effect on 0, but if we have a 1, then we shift it left. A bitwise shift left is the same as multiplying by 2. 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on. And then once we've multiplied it by 2, we transfer A to X, the index register, and then we can load from the pattern pointers table, here, X, and save it in the pattern pointer. And then we can load the second byte, the high byte, from pattern pointers plus 1, comma x, and store that in pattern pointers +1. Okay, so I think we should jump ahead to the pattern pointers table so that this makes more sense. Okay, so here they are, the pattern pointers. Now this is a table of words, so each of these is a 16-bit address. So that's why we multiply by 2, because each of these is 2 bytes. The pattern numbers is 0, 1, 2, 3. We have to multiply by 2 so that 1 becomes 2, 2 becomes 4, and so on, to account for the fact that each of these pointers is 2 bytes rather than just 1. So each row has 6 different patterns, and there's 5 rows. So 6 times 5 is 30. And they each have a name, like pattern A, pattern B, C. And you see how we skipped, as we discussed earlier in the previous video, there's no pattern J or K or pattern W. So these are our actual pattern definitions. So you see that pattern A, the first 2 bytes are the width and height of the pattern. So it's just a 1-by-1 pattern. So therefore it only needs 1 actual pattern byte. Starting at the 3rd byte is the actual pattern, and 0 represents pointing down and to the left, that tile. Okay, so pattern A, that's really easy. Pattern B is a 1 wide by 2 tall pattern, and the 2 bytes, the top one is 0, pointing down to the left, and 2 is pointing up and to the right. And we don't have to go through all these, but pattern C is a 2 by 2, so therefore we need 4 definitions. So 0 is pointing down and to the left, 2 is pointing up and to the right. That's the first row. And then the second row is 2 and 0. So that's how we arrange them. You go top left. It's just like screen memory where it works across and then down. And if you see, if we go all the way down here, here's some really big definitions like, they're like pattern 3 is 10 by 10. And then, so I've actually separated them out each into their own row. So that's 10 bytes, 10, 10, 10, 10, 10. That's the full definition. And this one is the biggest one. It's a 12 by 12. And you can see that has all 12. You see how we've put the size on their own line. It doesn't have to be like that. On some of them, I just crammed it all together like a smaller pattern, like pattern A. Yeah, it just seemed tidier to me to keep it all in one line. But you can do whatever you like. Okay, so the pattern pointers point to each of these individual definitions. These individual definitions are of varying size. So the reason for this pattern pointer is that we can't just use math to find the beginning of each pattern definition. This table allows them to all be linearly available, 2 bytes each. We just multiply by 2. We can find a pointer to the beginning of the address, and then these can be any numbers. They don't even have to be sequential memory at all. Of course, we did put them all one next to each other. You see, like one definition, this definition only takes 3 bytes. This one takes 4, 6. It's kind of like, these are basically 2-dimensional arrays where we give the width and the height of the array. And this is basically a 2-dimensional array, even though it's all linear. This is the first row, this is the second row, but they're of varying lengths. So that's why the pattern pointer solves that problem. So that's part of why I made this in assembly, and I'm explaining it is to show how we can take a sort of like a bit more of a complicated data structure. You might wonder, how do you represent that in assembly language? Well, this is how you make up a table of pointers that points to the actual data that can be of varying sizes. You can even get a more complicated data structure if you want. Building upon these principles, you could even have pointers within pointers, pointers within these definitions. That's totally doable, but it wasn't necessary for this project. Okay, so back to the actual rendering. Okay, so we've looked up the beginning of the pattern and stored it in pattern pointer. now that we have pattern pointers set up, pointing to the beginning of the definition, we're going to get the pattern width and height. So we load Y with 0, and now we're doing this indirect indexing mode. Pattern pointer is a 0-page 16-bit pointer to the beginning of the pattern, and we set Y to 0, so we get the very first value in that pattern, and we load it into the accumulator, and then we store it in the pattern width. So we'll save it there to work with. So like we're looking at that table, the first value is the pattern width, then we increment Y, and we load again from pattern pointer. This time 1 is added to the address. It looks at this address. This is pointing to the beginning of the table, but it adds 1 to the address. So that will be the pattern height. Okay, now we've extracted the width and the height of the pattern and saved them in pattern width and height. Next, we want to point to the actual pattern data. I guess I could have put the word data here. So what we want to do is skip over that pattern width and height that we've already got. Well, you could just increment Y, but it's a lot cleaner. Now that we've got the width and the height, let's just point right to the beginning of the data. So we clear carry. That's what you have to do whenever you set up for an addition. We're going to load the pattern pointer. That's the low byte of the address. We're going to add 2 to it and then store it back in pattern pointer. And we're also going to store it in pattern low. This is like a backup copy of the low byte of the pattern pointer. The reason we're doing that is because the pattern is going to wrap around. We're going to be pointing to different rows in the pattern, but once we get to the bottom of the pattern, we need to restore back to the top of the pattern. And so we're just doing a backup copy so we don't have to do these calculations over and over again. Then we're going to load the pattern pointer high byte, that's +1, and we're going to add with carry 0. Now it seems silly, but it's adding 0 but with the carry. So you have to keep in mind when the low byte gets up to 254 or 255 and you add 2 to it, it's going to wrap around to the next page. That is, the high byte is going to change. And so we have to bring that carry through. If you don't do that, then you'll get an error where the pointer is actually pointing back 256 bytes from where it should be. So this is kind of inefficient. You can do a branch if carry clear and skip some of this, which executes faster. But I don't like those extra branches when, like this isn't a timing critical area here anyway. So it's just cleaner to just do it this way, in my opinion. And then once we have the high byte calculated, we also store that in pattern high. Okay, so we have a pointer pointing to the beginning of the pointer data called pattern pointer. And we have a backup of it in pattern low and high, the 2 bytes of the 16-bit address. Now we're going to initialize some variables for the draw. We're going to set screen X and Y to 0 because we're going to be at the top left corner of the screen. And pattern X and Y are also going to be the top left of the pattern at 0, 0. Now, of course, some patterns are only 1 byte, so it seems like overkill, but we have to be able to accommodate different size patterns and then make sure that it handles that case of just a 1x1 pattern. Okay, and now we have to also initialize the screen pointer, which is going to point initially to the top left corner of the screen. So we load in the low byte of screen memory, which is, well, it's from 0400, 1024 decimal, or 400 hex. The low byte, we put in the screen pointer low byte. The high byte, that's what that symbol means there. Take the low byte or take the high byte of a 16-bit address and then store it in screen pointer +1, which is the high byte. Okay, so we've got everything pointed. We're pointed at the screen. We're pointed at our tile. Time to start drawing. So here we are in the draw loop. So we load into the Y register pattern X. X is going to start 0 and increment to accommodate a wider pattern. And then we're going to load from address pattern pointer offset by Y. We're always pointing at the top left corner to start with, and they're going to add the offset of Y, which is pattern X. So that gets the actual pattern value, just 0, 1, 2, or 3. That's the tile, what direction it should point. We're going to transfer that into X, and then we're going to look up in our tile table. These are the actual Petsky screen codes. We're going to translate X, 0, 1, 2, or 3, into those codes we had seen earlier. So now the accumulator actually has the screen code. I guess we could have just put these screen codes directly in all that data we were looking at earlier instead of 0, 1, 2, 3, but that just would be messy. I'm happier doing that at runtime. It's fine. It's fast enough. Okay, then we have to load Y with the screen X. So we also have that screen X that follows across the screen. And once that's in Y, we can store the screen code in memory, pointed at by screen pointer plus Y, indexed by Y. Okay, so we have the first tile plotted to the screen. Now we have to advance in our pattern to the next column. So we just increment the pattern X, but we have to check, is it still valid? So we have to load that in now that it's incremented, and we compare the pattern X to the pattern width. Pattern X of 0, now it's incremented to 1. We're going to compare that to the pattern width. Now, branch if carry clear is the same as branch if less than. So if the X is less than the width, then we're done. We can just move to the next screen column. But if the X has reached the width, then we have to reset X back to 0 so it wraps around, because that's what we want. While we're drawing the pattern across the screen, we want to repeat whenever we reach the width, then we go back to column 0. So if the width is just 1, you can see every time it's incremented from 0 to 1, it reaches the width, it gets set back to 0, 0, 0, all the way, 0, 0, 0, all the way across the screen. If the width is wider, then it'll do 0, 1, and then when it hits 2, for example, if the width is 2, then it gets back to, so then it'll toggle 0, 1, 0, 1, 0, 1. Or a really big pattern, like our 12 wide one, it'll go 0, 1, 2, 3, 4, 5, all the way up to 11. Then when it goes to 12, it'll wrap back to 0. Okay, so that's what all that does. It handles the pattern in the X direction. Now, we have to advance across the screen as well. We're going to increment the screen X, and just like before, we load the screen X, and we compare it with the screen width, which is 40. Now note that we have to put the number sign in front because screen width is not a memory location. It is just a label equal to a literal 40. So we want to actually compare to a literal 40, not location 40. So that's why I have to put this number sign in front. So we can check again if branch if carry clear. It means if branch if less than, if we haven't reached the end of the screen, then we can just branch back up to draw loop up here. Okay, so that's all the code it takes to do that repeating pattern across a single line, 40 characters worth, until it reaches character 40. And if it's not there yet, it just goes back to draw loop. Okay, so we're done one line. Now we are done a screen row. So what we have to do is reset both pattern X and screen X back to 0. We'll just do that first so it's out of the way. We're back at 0 for both the pattern and the screen. Now we have to point to the next row in the pattern. So we clear carry, we load the pattern pointer, and we're going to add the pattern width to it. So if it's too wide, then we're going to advance those 2 characters so we're pointing at the beginning of the next row. And just like before, another 16-bit address, we're going to store, after we've added it, we store it, then we load the high byte and add with carry 0 and store that in the high byte. That's just the same as we did with the 16-bit address before. So we're just pointing to the next row of the pattern. Now, we have to make sure, is that still a valid part of the pattern? So we increment the pattern Y. And then we load it, and we compare it to the pattern height. And if it's less than, we are fine. We can branch ahead, branch if less than, to the next screen row, which is down here. Okay, so that's if for a multi-line pattern, or if we haven't reached it, if we haven't reached the bottom of the pattern yet, then we can just continue on the second and third and fourth and so on rows of the pattern. But if we have reached the height of the pattern, if the pattern Y has reached the height of the pattern, then we have to wrap the pattern around, so we have to reset it. So first of all, we load A with 0 and put that back in pattern Y to indicate we're going to be back at the beginning, at the first row of the pattern. And then we take that backup we talked about, the pattern low, and put that in pattern pointer. And we take pattern high and put that in the high byte of the pattern pointer. Again, that's why we stored those back. I call them backups, rather than having to recalculate the beginning of the pattern every time through. We just stash a copy of it, and now we're ready to go for the pattern to repeat. Okay, so we've taken care of the pattern. Now we have to advance to the next screen row. So you see how the logic is happening at two levels here. You got the pattern and you got the whole screen. The pattern is kind of like a mini screen that keeps getting stamped down in between. There's lots of recurring, kind of repetitious code here. Well, at least you can see the same concepts over and over again. So again, we're going to do a 16-bit add. We clear carry, we load the screen pointer, and we add the screen width. So yeah, to move it to the next screen row, because it's 40 characters across, screen memory is actually linear. It's 1,000 characters, but the first 40 characters are the first row, the next 40 are the second row, and so on. We have to add that screen width to advance to the memory locations for the second row. So we add screen width, and we store that, and again we have to deal with the high byte, add with carry 0, and it's just if carry happened to get set here, and that'll happen about every sixth line. That's 6 times 40, 240. Every 255 characters, there is going to be a carry 6 and a bit lines. And now we have to increment the screen Y. And again, then we load it, and we compare that with the screen height. And we branch if carry clear, that is branch if less than draw loop. So if we haven't reached the bottom of the screen, we go all the way back up to draw loop, and we draw another row. And that happens 25 times with that pattern resetting as often as needed, and then the whole screen is done. Okay, now we're almost done. So when it finally gets here, that means that the draw is totally done. We're going to call this kernel routine FFE4. That checks for a key press. If it's just equal to 0, if it returns a 0, then we just loop to key wait. So that's just an endless loop waiting for a keystroke. So that's why I press return or whatever to advance to the next number. If there is a keystroke, then we go to the next pattern. So we increment pattern number from 0 to 1 or 1 to 2 and so on. And then we load pattern number and we compare it. Have we reached the total number of patterns, which is 30? If it's less than, then we're fine. But if it has reached the end of the list, we want to wrap back to the first pattern. So all you do is load A with 0 and store that in the pattern number. It goes back to 0. And no matter what, it comes back to this point where we jump back to init draw, which initializes the draw routine and draws the next pattern, whatever pattern number is set to. Okay, and now here we are again at those pattern pointers. There's all 30 pattern definitions or pointers to the definitions. Here's the actual pattern definitions. Patterns 1, A through Z, and patterns 1 through 6. 30 in total. Okay, so did we break that? Back arrow 3. back arrow 1, and we'll run it. Okay, and there it is. So that's a 1x1 pattern, 1x2, 2x2, and so on. You can just see the pattern just repeats and it fills the screen. Okay, so I hope you find that useful, how we do the data storage, how the drawing is done. And this has applications for games and all sorts of other things. Again, it's not as optimized as it could be, but I didn't think that was a priority here. I want to just show the general process. Sometimes tiles like these are used in video games. That's how you make a great big scrolling map, or even like a static screen. They're often built out of tiles. So the tile might be 4x4 characters, but rather than just one tile repeating like we're doing here, you would have quite a few different tiles and you build the screen. The reason games use tiles is because you can make a much bigger world by building them out of these blocks. Instead of building them out of just 8x8 pixel characters, you can build them out of these blocks where you might have, 16 different characters that create one bigger tile, and then you build your whole world out of those repetitious tiles. Just while editing, I thought I'd add just a little bonus comment here. This is my game, Minima Reloaded. This is version 1.2. I coded the original back in 2001 for a mini game competition with some help from my friends Steve Judd and Per Olofsson for the music and graphics respectively. And then I've upgraded it a few times over the years, but basically it's a tiny little RPG. The original fit in just 2K, not 2K of RAM, but 2K file size, and then this Minima Reloaded bloated it up to about 4K. I think it's 15 blocks. And so it uses a combination of procedural generation and tiles, like we were just talking about, just 2x2 graphic tiles, 2x2 characters. So 4 characters are combined into a single tile. But what I didn't make clear earlier is that just one byte can choose the tile. So therefore you can get 4 characters worth of graphics for just 1 byte, which is a huge savings when you're building a world. Of course, the cost is that there's a lot more repetition in the world, but for a lot of games, that's a perfectly acceptable trade-off. So the procedural generation makes a map that's 256 tiles wide, 96 tiles north to south. Then you kind of double or actually quadruple that when you go from tiles to characters. Multiply that out, that's almost 100 Commodore 64 screens worth of world to wander around. I think it's like 98 or something. Pretty amazing for just a 4 kilobyte game. And again, that's not just the tiles, but it's the combination of tiles, procedural generation of the map, and the fact that the Commodore 64 has lots of RAM, so I could render that relatively large map into RAM each time the game starts. So anyway, that's just another application of tiles with pretty similar code to what I just showed. Maybe someday I will do a walkthrough of this game, although that would be hours and hours worth of explanation if I was really to do it in depth. Okay, back to Robin of the Present. Okay, thanks very much to my patrons for their support. Thank you for watching, and we'll talk to you next time.